Hello, I'm Lena Heidemann and I work as a researcher at the Fraunhofer Institute for Cognitive Systems. In this video, I'd like to present our work on concept correlation and its effects on concept-based models. Firstly, I'll give a short introduction into concept-based models in general, then I'll explain the motivation for this paper, and lastly, I'll give an overview of our main contributions and results. So let me start off with a quick introduction into concept-based models. The main idea is to directly learn high-level concepts in an intermediate layer and then use these concepts to predict the main class. As an example, based on an image of a bird, the model would predict concepts like the shape, length, and color of the bird's bill, and then use these concepts to classify the bird species. One example of these types of models are concept bottleneck models. They achieve competitive accuracy with standard end-to-end models while enabling interpretation in terms of high-level concepts. However, it is difficult to verify that the output of the concept model is truly based on the predicted concepts in the image. Now, this brings me to the motivation for this paper. We started to evaluate concept models by removing parts of a bird from an image. So we can see here in the figure that the concepts are still predicted with high confidence, even when they are no longer visible in the image. This example shows that concept predictions may not be based on the actual concept in the image. We also saw in real-world datasets that many concepts almost only appear together with another concept, so they are highly correlated. Putting these two together, such high concept correlations would allow the model to predict a concept with high test accuracy by simply using a correlated concept as a proxy. That means without having learned what the concept actually looks like. This issue motivated us to investigate the effects of concept correlation further and make the following contributions in our paper. Firstly, we propose evaluation methods beyond test accuracy for evaluating if concept-based models have truly learned to detect a concept. Second, we analyze concept correlations in two real-world datasets and investigate their potential effects on concept-based models. And third, we present simple mitigation techniques like loss weighting, which yield promising initial results. As we don't have time to go through all of the experiments, I'll just give a short overview of our main results. In terms of concept correlation analysis, we see that concept models struggle to learn highly correlated concepts. Also, using datasets of 3D shapes, we show that for at least one concept of a correlated pair, the model's performance decreases with higher correlation and with less training data. We also show that there may be side effects of concept correlations on other seemingly unrelated concepts. Regarding mitigation techniques, we demonstrate that these side effects can be contained by training one model per concept instead of using a shared model. And we also show that the model's performance can be improved by putting more weight on the loss of samples where only one of the correlated concepts is present. Now, due to time constraints, I can't go into further detail here, but I'd like to invite you to have a look at our paper and feel free to contact us for questions and feedback. Thank you.